From a rest at set position to crossing the finish line at a speed of 30 to 40 kilometers per hour, an elite sprinter only takes about 10 seconds. During each phase in a sprint, the sprinter takes different stances. The coordination of various parts of the body, muscles and bones helps him move forward. When you watch a 100-meter sprint, I think you can notice that there are in general 4 phases, including crouch start, acceleration, maintaining speed, and deceleration. To win a 100-meter sprint, one of the tricks is to react quickly to a cue. In short, reaction time is the time interval between detecting a signal from the horn or a starting gun and responding to it. In a world-class contest, sprinters generally have a reaction time of about 0.15 seconds. If a sprinter's reaction time is even 0.1 second longer than the others, he might be a few steps behind. Now let's look at the force involved in running. The sprinter's left foot is currently in the air. The sprinter's right foot exerts a force on the ground in a backward direction. We call this an action. You may refer to the red arrow. According to Newton's third law of motion, action and reaction always come in pair with equal magnitude, but act in opposite directions and on different objects. Simultaneous to his backward action onto the ground, a force of equal magnitude known as reaction will be exerted on the sprinter's foot by the ground in the forward direction. As the reaction is in forward direction, the force exerted by the ground pushes the sprinter forward. Since a 100-meter sprint only takes about 10 seconds, sprinters need a very strong and fast start, so as to shorten the time they need to reach their maximum speeds. Professional athletes adopt a crouch start with starting blocks to achieve the fast start.
It was heard that many years ago in 1888 there was a sprinter. He discovered that when a person started from a crouch position, leaning forward, the reaction time could be shortened. At that time, there was no one starting from a crouch position or any other positions. They all liked to use a jogging position, with 1 foot forward and 1 foot behind. Then, somebody found that when starting with a crouch position, the sprinter leaned forward. There's a tendency to slide forward. It enables the sprinter to accelerate at the start. Then, in the world of sports science, as time went by, the researchers and the sprint coaches found that the sprint start with a crouch position, so far, is the most suitable one for sprinters to use. Then, another topic of a sprint start is the introduction of the starting blocks. In the Olympic Games, the formal use of starting blocks started in the London 1948 Olympics. When we have the starting blocks in the world of sprinting, including the 100, 200 and 400-meter sprint races, we can shorten all the reaction time of the sprint starts. Naturally, for all sprinters, it makes their performance improve greatly.
The starting blocks help sprinters to stay in the crouch position and to lean forward. Compared with the standing position, crouch start allows the sprinters to exert a greater force onto the starting blocks. In the clip, the sprinter starts to run from a crouch start, exerting a strong action on the starting block. See the red arrow in the clip. According to Newton's third law of motion, the starting block exerts a reaction with magnitude equal to the action exerted by the sprinter onto the starting block. See the blue arrow in the clip. The reaction force, in blue arrow, is comprised of 2 components: a horizontal component, in yellow arrow, and a vertical component, in green arrow. The vertical force lifts up the sprinter's body, but doesn't help him to move forward. It is the horizontal force, and yellow arrow that pushes the sprinter forward. Have you noticed that starting blocks are usually set at an inclined angle in a competition? Do you know what is the rationale behind?
For starting blocks, we have to think about the factor of individual differences, because we know people are different in their body types, like height, the shape and length of their legs, body size, body shape, trunk length and foot length. According to the guidelines of the International Association of Athletics Federations, when we use starting blocks for a sprint race for the front leg, it should be 90 degrees at the knee. But when it comes to the rear leg, it can allow for a wider range for changes. The range can be 120 to 140 degrees. But there's no such angle of the rear leg that can suit all sprinters in the world. We can see that among all sprinters, they're totally different in height and size. That's why we need to try. Then you can know which angle of the knee would be most suitable for you.
Assume that a foot applies 300 Newton of force. Let us denote it as F, to a starting block that's set at an angle of 30 degrees to the ground. What is the magnitude of the horizontal reaction generated that pushes the sprinter forward? To find the horizontal reaction exerting on the sprinter, let us first resolve the force F into two parts: the horizontal reaction, Fx, and the vertical reaction, Fy. And then, to find the horizontal reaction, Fx, by trigonometry. Fx divided by the force F equals to sine 30 degrees. F is 300 Newton. After some calculations, we get that the horizontal reaction Fx of 150 Newton pushes the sprinter forward. If the starting block is adjusted to be more inclined at an angle of 60 degrees to the ground, what is the magnitude of the horizontal reaction that pushes the sprinter forward? With trigonometry, we may also find the horizontal reaction Fx using the same formula as before with a larger angle of 60 degrees. Fx divided by force F equals to sine 60 degrees, where F is 300 Newton. After calculations, wow! Once the starting block is adjusted at the larger angle of 60 degrees to the ground, the horizontal reaction is almost 260 Newton. This is almost a 70% increase over the horizontal force generated at 30 degrees. After leaving the blocks, sprinter accelerates during the first 20 to 30 meters. This phase is called acceleration. To understand how sprinters accelerates on the track, let us first understand the relationship between force and acceleration. From experiments, scientists assert that the force F applied on an object is proportional to the acceleration A of the object. The greater the force applied, the greater the acceleration. On the contrary, the greater the mass of an object, the stronger the force that is needed for the object to reach the same acceleration. That means the force F applied is proportional to the mass m of the object. Combining these two proportionalities, we can see F is proportional to ma, which means that the force applied is proportional to the product of the mass and the acceleration of an object. The unit of force is Newton, abbreviated to N. It is defined as a force that gives an acceleration of 1 meter per square second to a mass of 1 kilogram. The above formula can be written as F equals ma. This is Newton's second law of motion. The energy that allows a sprinter to accelerate comes from chemical reactions inside the body. If 240 Newton of horizontal force is applied on a sprinter of 60 kilograms at 10 meters away from the starting point, what is the acceleration of the sprinter at that time? Neglect factors of wind resistance, running posture, and so on. Let us use the formula. A equals to F divided by m. Let's substitute the relevant figures into the formula. The force, F, is 240 Newton, and the sprinter's mass, m, is 60 kilograms. The forward acceleration of the sprinter at that moment is 4 meters per square second. If the sprinter is lighter, say, with a mass of 50 kilograms, what is his forward acceleration? Substitute the relevant figures to the formula and calculate. This time, the sprinter's acceleration increases significantly to 4.8 meters per square second. We have learned that sprinters accelerate at the initial phase. However, sprinters cannot keep accelerating indefinitely due to human limitations, such as building up of lactic acid in their legs. Near the end of the acceleration, the sprinter runs at his maximum speed of 8 to 12 meters per second, and then enters the next phase. In this phase, the sprinter maintains the uniform speed. Whether the sprinter can maintain his maximum speed mainly depends on 3 factors. First, wind speed. Wind speed can hinder the performance of a sprinter and cannot be taken lightly. Simply speaking, the presence of a tailwind, which is in the same direction as the sprinter, assists the sprinter. The presence of a headwind hinders a sprinter. Because the presence of tailwind assists the sprinter, a record-breaking time in any international outdoor event will only be considered as official if the wind gauge reading indicates a tailwind of no more than 2 meters per second. Researchers show that the advantage of 2 meters per second tailwind is about 0.1 second in a 100-meter sprint. Second, frictional force. Whenever one object moves or tries to move another object, there is friction acting between the two surfaces in contact, and this opposes the motion. In some cases, friction makes movement difficult, while in other cases its presence is essential. The magnitude of friction depends on the smoothness of the surfaces. Simply speaking, the rougher the surface, the greater the friction.
In sprint racing, the spikes we wear can be a very critical factor. In sprinting, we'll step on the ground with the front sole of our foot. When we push off the ground, we can have the right movement. According to Newton's third law of motion, when we push our foot against the track, it'll make us have the greatest reaction for moving forward. It makes us have the best running form with our stride pattern and posture.
So when a sprinter accelerates, he steps on the ground harder so as to increase the friction between the sole of his shoes and the ground. Having planted and gripped on the ground with his left foot, the sprinter can exert a force on the ground. The reaction from friction of the ground in turn acts on the sprinter's foot in the forward direction and allows him to move forwards. In this time, the sprinter's right foot grips onto the ground, and the reaction generated from friction allows the sprinter to move forward. If a sprinter runs on a wet track, the contacting surfaces are wet. The frictional force becomes smaller. As a result, the speed would be greatly reduced. Third, wobbling of the center of mass. Any object has a center of mass, cm. This is a point at which the entire mass of the object behaves as if it was concentrated. Under normal conditions, the center of mass coincides with the center of gravity, Cg. We can use a plumb line to locate the center of gravity of an object. Since the center of mass is a specific point where all masses behave as if they were concentrated, it is also the point of which we can balance an object. I can use a finger to hold the plate as its center of mass. However, our bodies are not regular in shape. When we change our posture, the position of center of mass changes as well. When I stand straight like this, the center of mass is approximately located at my navel. As he runs, the stance of a sprinter changes, So the position of the center of mass also changes slightly, indicated by the orange points. To a sprinter, the wobbling up and down of a center of mass is not desirable because some of the sprinter's kinetic energy will be changed into potential energy, which reduces the kinetic energy available for running forward. When the center of mass of a sprinter wobbles upwards, the energy undergoes the following change. Kinetic energy after wobbling upwards equals kinetic energy before wobbling upwards minus potential energy. That means the potential energy increases whenever the sprinter's center of mass wobbles upwards, but at the expense of his kinetic energy and forward speed. The sprinter has to stride even harder onto the ground to maintain his speed, and this will make him tired sooner.
In science, we have a term called momentum. Momentum is measured as the mass, that's to say our weight, multiplied by the speed. As we know, the momentum factor can affect our performance in sprint races. In the case of sprinting, we need to have a powerful motion of our arms. It can increase our momentum, making our body dash forward, and we move even faster. In the case of swinging our hands, we should try to keep the balance while moving forward. When we move our hands, we have a force of rotation at our shoulders. But we should try to avoid rocking our body sideways. Instead, we should keep swinging our hands to the front. Then we can keep the balance between the two sides of the body. We should make sure we avoid any rocking of our body. Just keep the straight line. If we have less rocking, we won't waste our energy. It makes all our propelling energy turn into forward motion, ensuring that we sprint as fast as we can.
The final phase of a sprint comes in which the sprinter decreases speed after breaking the tape and finally coming to a stop.
Sprinters cannot come to an immediate stop after breaking the tape because an object tends to remain in its state of motion unless an external force acts on it. This tendency is called inertia.
Even if the sprinter's foot can stop, his upper body will still move forward. It leads to a loss of balance and makes the sprinter fall over. Newton expressed inertia in his first law of motion, which states that an object will stay at rest or move in a straight line at a constant speed unless an external force acts on it. Owing to the inertia of the body, the sprinter continues to keep moving forward after breaking the tape. However, after the race ends, the sprinter does not need to push hard on the ground. Meanwhile, the frictional force between the track and the sole of the sprinter's shoes gradually slows him down.